Hey there, team. It's Mr. Ramirez. So I'm gonna split up your questions in two videos, just 'cause I feel maybe I will. We'll see. Just because I feel it might be a little two different subjects, and I don't want to throw too much at you in one video. First, we're gonna start with these oxidation reduction equations. This stuff I know looks pretty stupid and a little complicated at times, but I promise you it's pretty easy. So let's just dive right in with the first part A here, right? So does the reaction show oxidation reduction? So despite this word's combination and sounding, it doesn't mean a reduction in oxidation. They're two separate things. There's oxidation and there is reduction. So we'll look at the equation up here, okay? And we'll figure that out. So the first thing you'll probably notice is this looks like a normal equation in chemistry, except for these numbers up here. That is because that is their electron state. That is their charge, pretty much, of each individual element. So we look at aluminum, for example, right here. We see aluminum is sitting there with a zero charge. So we have aluminum at zero charge. Hydrogen on this side has a +1 charge, and chlorine has a -1 charge. After it reacts, however, aluminum has a +3 charge now, chlorine still has a -1, and hydrogen now has a 0. So we notice that the numbers don't match up, right? So aluminum, right, has a 0 and it gets to a 3. Hydrogen has a 1, it turns it to a 0. So what that indicates is there is both reduction and oxidation. Now what's the difference? Reduction, let's identify each one, all right? Let's start with oxidation. So here we see aluminum, right, has a 0 charge. It has a 0 charge here. Let me zoom in a little more. Aluminum has a 0 charge, right? Actually, I can even get closer. Haha, perfect. Okay, so aluminum has a 0 charge, right? So it goes from a 0 charge to a +3 charge. Now, how does it do that? It loses 3 electrons. As we know, electrons, that's not how you spell electron. Oh my good lord. Please mind my handwriting. I am using a mouse. Let me try to... Sometimes if I can't do E's, and I'll do a capital E. Electrons. So as we know, right, electrons are negative, right? I don't know why I have to write it out for you. I don't know. It's bugging me not to. So electrons are negative, because I'm going to erase it anyway. I'm not firing all cylinders, am I? So we know electrons are negative. Point being, right? So for 0 to a +3, if it loses 3 electrons, its charge goes up to a +3. And when a charge goes from a lower number to a greater charge, that is oxidation. So we know aluminum is experiencing oxidation. So what about reduction? Well, reduction is the opposite. Reduction is when a higher charge, hint hint, turns into a lower charge. So we see here hydrogen goes from a +1 to a 0. That indicates reduction. Its charge has been reduced. So, does it show oxidation reduction? Yes, it does. And that's how simple it is. So now we're going to get to the next part, which is writing out the equations. So if so, write the oxidation and reduction half reactions. Now that seems difficult. It's actually pretty easy. It's just different language. A different way to write it. So let's start with, I like to start with the reduction first. And with reduction, we put in red. So we'll keep it red. So we'll just call this the reduction, right? The reduction. So we said hydrogen, right? So we write out the whole part of whatever hydrogen's attached to. HCl reacts, and it created H2, hydrogen gas. And we know the charge for hydrogen on this side was a +1. Chlorine was a -1. And over here, hydrogen now turned into a 0 charge. Now, to write a reduction, all you have to do is write out what's happening with the electrons. Now, if hydrogen is gaining an electron to become 0, gaining a negative charge to make it 0, all we have to do is write that in. +1, chlorine, is that a -1? Plus, and this is where it is, plus an electron. I believe I wrote that backwards. It's supposed to be an electron like that. That's how it's supposed to look. And that produces H2 with this, not H2O, H2 with a 0 charge. And that's it. That's how you write your reduction half reaction. That's all you do. That simple. So now we're going to go to the oxidation. Now the oxidation is a little bit different. It's very similar, but it has a stark difference to it. So we're going to go, right, we're going to write the equation out. Al, aluminum, with the 0 charge, react to create AlCl3. AlCl3 with a positive 3 charge and a negative 1 charge, right? So now we got to write out the equation very similar to how we did down here, but there is a difference. Instead of on the left side, we're going to write the electrons on the right side. So, right, we have the aluminum with the 0 charge, reacts to create this AlCl3, negative 1, positive 3. However, how many electrons is it losing, right? So if each electron counts as a negative 1 charge, this side, is when it reacts, is losing 3 electrons. So on this side, all we gotta do is write like this. I literally keep forgetting. It might be I literally have done this 1,000 times in my life, and I can never remember whether the negative sign comes first or the E comes first. I think it has to be. Oh, sorry. So right, so we have this. We said it gains 3 electrons, so it should be plus 3 E negative. That's it. And there you go. You got reduction half reaction and your oxidation half reaction. There you go. That simple. So now we're going to move on to section C, right? Or part C. So from the table, would these reactants form these products, et cetera, et cetera. So pretty much all you got to do is look at this table here, and let's find aluminum, all right? So we go look down, look down, look down, aluminum, all right? And this is saying it's an oxidation reactant, right here. Oxidation agent, reducing agents. So we see aluminum 3, right? Do we have that? Aluminum with a plus 3 charge? We do. And across the board, it's just regular aluminum with no charge. Yes, we do. So yes, these would. And they would because they are very similar in relative strength. It's pretty much what it means. It's that aluminum is really, really, really wanting to give away, not give away, should I say. It's actually wanting to accept. Oxidation really gains charges, so it's trying to, how do I put it? Please mind my buffering in real time. Let's see. How do I put it? It's difficult to explain more in that some elements are more keen to. It's called their electro. I believe it's called their electronegativity. It's where each element has a instinct want to either give away an electron or to take electrons to get to that magic number of 8 electrons in order to have a full ring, a full ring of electrons around it. So if we just look there, we see that aluminum right here. It's very likely that aluminum is going to oxidize into aluminum 3. That's pretty much all you have to look for in this chart here. And I don't know if I see HCl here, or even do you even see hydrogen? I mean, you see hydrogen and gas. I mean, you see Hg, but that's not hydrogen. It should be. Here we go, H2. There we go. Look, right here. Perfect. See, we have H positive here. That's really what we had. We had H with a positive charge, right? If you see on the right here on the graph with that H, the H is just a positive, there's no number. That just means it's a positive 1. And if we look back at our original equation over here on the left, H plus 1 will react to create H2 with no charge. So yeah, just from this table, we can assume, yes, they are, because they have a very similar strength of electronegativity. I would write that out, but my mouse does not permit me to write very big words neatly. So that's that. Now, this is the part that gets a little different. This balancing equation thing here. I have asked my friend who's a chemistry major up at OU. I even sent an email to a professor of mine, and I asked him, what is the electron transfer method? They could not really tell me. They had some ideas. Each one had a different idea. One just assumed it was just balancing while showing the electrons, the electro charge up top. Another one was a very complex method that I've done before, and it's very, very complex. That's the difficult part. And they didn't give you a lot of room to work that in, so I would have to say they're not trying to ask for that. So we're just going to balance it regularly, we're just going to balance it the regular way that I know how. And I'm going to send you a video of the more complex way. It's actually how I learned it as well. And if you could also send me a photo of where in the book they teach you this electron transfer method, because I don't think it is what I think it is, and I don't have the books with me, so I can't really tell you. So if you could send me a picture of whatever this means, because I'm not sure. But so we're just going to do it really quickly the regular way, because we'll see if that happens. So our original equation, right, was AL plus, ooh, I gotta write neater even though I don't like doing this. Okay, I find putting my whole arm on the table helps. Okay, undo. So we got AL, and I was wrong, it does not help. AL plus HCl produces AlCl3, aluminum chloride, plus hydrogen gas. And we could put the numbers up here, but it's not really worth our time at the moment. Actually, it might yield something interesting, so we might as well. So we got 0, we got a +1, right, and -1. Now here we got a +3, and a -1, and a 0. There you go. So, and we'll split this down the middle. And so, with balancing equations, we know it's just about getting the numbers on both sides to be equal per element, right? So we have on this side, we got aluminum, right? We got hydrogen, and we got chlorine, right? And same thing over here. Those are the elements we're working with. So on the left side here, we have 1 aluminum, 1 hydrogen, and 1 chlorine, right? On the right here, we have 1 aluminum, 3 chlorine, and 2 hydrogen. So it's obviously not a balanced equation yet. I'll make this a little thicker, maybe a little easier to read. So the thing about balancing equations that's useful is you got to think about lowest common denominators. Lowest common denominators are a very, very easy way to create ballparks and where you need to get. So if we look at all these numbers, what's the lowest common denominator each one of these has in common? The 1s, the 3, and the 2. 6, right? So we think, okay, we got to turn things into 6. So what's the easiest thing to turn into 6? Well, we'll start with the hydrogen 2, right? We know something times 2 equals 6. Well, it'd be 3. So we put a 3 there, right? We change the coefficient in front, and now we have 3 times 2 gives us 6 hydrogen. Awesome, right? So we have 6 hydrogen on this side. That's where we want to get to, our lowest common denominator. So we got 6 on this side. Now we look here, we got 1 hydrogen here. Well, how are we going to change that? Well, how we get 1 to turn into 6? We put a 6 here, right? And now we'll have 6 hydrogen and 6 chlorine. Now that leads to another issue. Our chlorine on this side is only a 3. Well, we can't have that, right? So how do we turn that 3 into a 6? Put a 2 into the coefficient. So now that'll give us 6 chlorine, but 2 aluminum. So now we just need to see, okay, our aluminum is 2 here on this side, and it's 1 here on this side. So what do? Well, we just got to change the coefficient one more time on this side to make it 2. And now we see all of our numbers match up. The equation is now balanced. So let's just write it out fully. 2 Al plus 6 HCl reacts to produce 2Al Cl3 plus 3H2. That easy. And that's it. That's how you balance the equation. Now, if we think about the charges, actually, there's one last step. We could think about these charges. So if we have 2 of a 0 charge, that should still be 0. If we have 6 of a positive charge, that should be 6. That should be a -6. Over here, we should also have a 6 charge. And the CLs are a -1, so we should have -6 and 3, 0. If you look here, if we add up the charges now, right, so 0 plus 6 is 6, 6 plus -6 is 0, 6 minus 6 is 0, plus 0 is 0. The charges up top, this is an important part. This may be what they wanted which actually I think about it probably is. They want these. It's literally just balancing the equation and then proving the charges are now equal as well. If we look, the charges are equal, right? Aluminum, so 0, positive 6, negative 6, that equals 0. 6 minus 6 is 0, plus 0 is 0. So the charges total on each side are 0. So this equation is truly now balanced. So yeah, that's pretty much how you do all these. I want you to try the other ones on your own and let me know how it works out. If you need more help, we can set up a time. Like I know you said you're practicing Ramadan at the moment. So if you need to, we can definitely set up a session at night where we can meet on Google Meets and we can screen share. And pretty much what it means is you'll see my screen, you'll see all this, and I can walk you through one in real time. And we can do it that way, or we can do another video, however you need help. So I think this is getting kind of a longer video, so I am going to make you a separate one for the for the half cell stuff, which is actually pretty easy. I'm thinking about it more. I was just say easy to show you. I just don't want to turn this into a 29-minute video for you. So I'll see you in the next one.